Good morning, everybody. Welcome to this plenary session. It's my great pleasure to introduce our speaker, Paul Hoyningen-Huene. Paul Hoyningen-Huene is, of course, very well known. He is emeritus professor at the Institute of Philosophy at Leibniz University in Hannover, where I am too. He is the founding director of the Institute of Philosophy in Hannover. He's also founding director of the former Center for Philosophy and Ethics of Science in Hannover, and he is now also Lehrbeauftragter at the University of Zurich at the Department of Economics and the Department of Philosophy. So Paul, of course, is well known for his work on Thomas Kuhn, his book Reconstructing Scientific Revolutions, and more recently his book, I think it was in 2013 that it was published, the book on Systematicity, the Nature of Science. And today, Paul will talk about a very classical topic in the philosophy of science, namely scientific realism, and the question that he will be addressing is, are there good arguments against scientific realism? Paul, yours.
Thank you very much. Thank you very much for the invitation. It's a pleasure to give a talk, an invited talk in Germany, which is rather rare. So I took a subject that I hope is a prominent one. Are there good arguments against scientific realism? And the prima facie answer is, of course, no. There are no good arguments against scientific realism. And the reason you may take here is that look at the top scientists who usually have a solid education, which is different, of course, from the education in philosophy, at least on the continent here. And they are usually diligent, rational, self-critical, and intelligent people, but in parentheses, at least as long as they talk science. I'm not saying they talk about science, but at least as long as they talk science. So I think this is undoubtable. And here are some data you might be interested in that a group of top scientists measured on September 14th, 2015, and the publication was on February 11th, 2016. So what's today? That's almost a month ago. We arrived in physics in the 21st century with the publication of this paper. What is it? So here are the data from the original paper. Is the LIGO collaboration on gravitational waves. That's two detectors, one in Hanford, Washington, one in Livingston, Louisiana, and that is what they measured. They measured the strain of these 4-kilometer long arms in these gravitational wave detectors, and the relative accuracy that they can measure is 10 to the minus 22. So we have here things of 10 to the minus 21. That's the noise, and that is the signal that they saw, and the signal was just very astonishing. And you find the same signal both in Hanford and in Livingston. Here is the two signals on top of each other. So the strain that they're measuring, these 10 to the minus 21, that's the equivalent to a hair width in comparison to the distance to the nearest fixed stars, Alpha Centauri, in 4 light years from here. It's 1 hair width in 4 light years. So I guess it's the most precise, by far the most precise measurements that physics can do, because in quantum electrodynamics, as far as I know, it's something like 10 to the minus 14 or 13 or something. So this is 10 to the minus 21. This is just absolutely smashing. Now, this is what they measured. These are the data, the raw data. They are almost absolutely raw. And then what they did is, in advance, they calculated some 200,000 different events from general relativity of possible events that they might observe. And this is this curve here. And then if you subtract this curve from that one, then the rest is the noise. That's the residual stuff. And that's a very interesting curve. And what you see here is the frequency of these oscillations is increasing, as is the amplitude. And you've got the same signal there. They are 7 milliseconds apart, corresponding to the 3,000 kilometers these two detectors are apart. So this is what they measured. This is a measurement, as I said, that's the beginning of the 21st century. In physics, for me, I've been in physics now for exactly 50 years, so almost immediately after my birth I started with all of that, and that's really the most significant event in my life as a physicist. So let's see, the interpretation of these data is the following, and now I quote from this paper. That's the original paper. It's a paper of 1004 authors. This is not a very huge paper. It's a big one, but it's not the biggest one. The biggest paper has something like 3,500 authors, but other people know much more about that than me from Physical Letters. That's the paper from February 11th with the press conference. And I go to the conclusion, and the conclusion is not differently formulated than the main body of the paper. So usually, very often you have hedging phrases in the main paper, and in the conclusion you don't have the hedging phrases, we're less careful. That's not the case here. So the conclusion is exactly the same sort of wording than you find in the main body of the paper. And here is what the conclusion is. This is a literal quote. I've got the original paper here if you want to have a look. The LIGO detectors have observed gravitational waves from the merger of two stellar mass black holes. The detected waveform matches the prediction of general relativity for the in-spiral and the merger of a pair of black holes and the ring down of the resulting single black hole. These observations demonstrate the existence of binary stellar mass black hole systems. This is the first direct detection of gravitational waves and the first observation of a binary black hole merger. And that event was rather dramatic because experimental evidence of observational evidence was only available for black holes of about 10 sun masses. What happened here is the merger of two black holes, one of 29 sun masses and the other one 35 sun masses. And the dramatic character of the event is this, that within a fraction of a second 3 sun masses were transformed into gravitational energy. And 3 sun masses doesn't tell you very much. It's 1 million Earth masses. And if you want to know what that means, if you transform immediately into radiation 1 million Earth masses, the amount of matter that was transformed into energy immediately with the Hiroshima bomb with some 20,000 equivalent of TNT was 1 gram, right? The largest hydrogen bomb ever exploded was 5,000 times stronger than the Hiroshima bomb, and that transformed 5 kilograms of matter in within in a very short while, of course, 5 kilograms. And this is 1 million Earth masses. The luminosity, to end now the big numbers, the luminosity of this event was 200 sun masses per second. That's more than the whole universe radiates. So it's just an incredibly fat event, and people weren't prepared to see that. But here you see, they describe it here. They have observed that. They demonstrate their existence. This is, of course, pure realism, what's happening there. And here I prepared for you, which was quite time-consuming, a little graphic here that you can see what is happening here. Wait a minute, here we go. This is the event. These are the two black holes, and what you find underneath is a two-dimensional representation of the four-dimensional space-time. And here they are circling each other at a very high frequency, 30 sun masses, and they're doing some 70 or 150 revolutions among each other. And you see the waves radiated down here. And now it somewhat becomes dramatic, and we can see it on Earth. Really a lot of work to do that, these graphics. And here you go. Now it's now here is the drama. Here they are merging, and here you've got the maximum of the radiation, and then we've got one black hole. And here you see the waves going out. This is from the merger with the maximum, and here the waves are going out. And it took them 1.2 or 1.3 billion years to reach us. So if you know that this goes with 1 over r. I'm sorry, I didn't do the animation. That is these guys. I'm sorry, I mistook that. This wasn't plagiarism. It was just a little mistake. But what you see here is Max Planck Institute for Gravitational Physics, which happens to be in Hanover. Happens to be there. That's it. Okay, and we gratefully acknowledge this and that support. So this is the event, and what you see is the case seems pretty clear. These intelligent, diligent, blah, blah, blah. Physicists, they have no hesitation whatsoever to interpret that event realistically. It's just absolutely no hesitation. No, in the light of general relativity, blah, 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 it's consistent with a... No, they simply say we observed that, right? They just saw the merger. I mean, for us as philosophers of science, oh, that's a very indirect kind of observation, but physicists are just, go straight to the matter. So the case seems pretty clear about arguments against scientific realism, namely from the point of view of physics. I mean, it's just not even a discussion. I mean, they just take it for granted. They saw the black holes, period, right? However, is that loud enough? Yes. Can you hear me? Yes, good. However, look at Stephen Hawking. He is a physicist. He's not a philosopher. You can't claim that. Here is he. And what did he say? I take the positivist viewpoint that a physical theory is just a mathematical model and that it is meaningless to ask whether it corresponds to reality. It's meaningless. It's not even false, right? It's meaningless to ask those. This is a very, very strong position. All that one can ask is that its predictions should be in agreement with observation. So that's very funny. So you may think, well, Stephen Hawking, what does he do? He's a strange physicist, well, Stephen Hawking, so this question is, of course, is this a contradiction? And that becomes even stronger if you look, how does Hawking's instrumentalist attitude fit with the typical realist stance of physicists? And if you know a little history, then Hawking has himself substantially contributed to black hole physics. Namely, he wrote, for instance, one article in 1971. This was immediately after the Joe Weber experiments, for those who know some context, namely gravitational radiation from colliding black holes. Exactly about that situation. And in that very early paper, he just computes an upper limit for the energy radiated by the colliding black holes, exactly the situation. So here, he seems to be fully realist, and when he talks about these things in general, he's fully instrumentalist, namely the most radical instrumentalism that you can imagine. He doesn't say the models are false or not even approximately true. No, it's meaningless to ask about the reference of theoretical entities. It just doesn't make sense to ask the question. A theory is just an instrument like scissors. You cannot ask the question whether the scissors are true. It just doesn't make sense. In the same sense, he says, it doesn't make sense to ask whether theory is true or false. It's just an instrument to produce productions. Now, the point is, of course, is this a contradiction? And in my pre-lecture discussions with members of this honorable conference, of course, people said this is a contradiction. And I had seen that before, Oh, I saw that. Yeah, that was a contradiction. Oh, is it? Well, now I suggest that one should distinguish a few different things in this connection. Namely, first of all, if you move within physics, then the relevant question concerning theoretical entities in our language is, the relevant question is whether particular theories allow a realist interpretation. Particular theories. You take one theory and then you ask, can I interpret that realistically? And for instance, you ask the question whether black holes or gravitational waves exist. You ask that in particular with reference to general relativity. You ask, do they exist? The general question about the epistemic status of physical knowledge in general is just irrelevant. Nobody asks this question within physics. Within physics, right? Within physics, okay? So, within physics, you do have a question about theoretical entities, but it's always a singular, particular question given in a theory. So you ask, for instance, today, do strings exist, right? And we don't know. So people settled these questions. So for instance, if you ask physicists, do quarks exist? Then physicists will say, yes, they do. They got a different mode of existence than normal billiard balls or so, but that's a different story. So within physics, the relevant question is whether particular theories allow a realist interpretation. However, also physicists, not only philosophers, may question the general epistemic status of physics. Are we generally allowed to interpret accepted physical theories realistically. So if you don't see that contrast that is alluded to here, I make it hopefully at least a little more clear that I think in how I try to express it, that there are 2 or even 3 different levels of what I call philosophical radicality. Right? You may become more and more philosophically radical and putting things into question which were unquestioned before, and that involves increasingly radical stances, and I give you 2 or even 3 of them. Now the stance 1 is that you say, I believe in common sense things, I believe in the sense that I'm not questioning in this sort of discourse, I'm not questioning, I just accept, yes, there are common sense things, and I believe in the accepted, realistically interpreted physics, and I question whether particular newly postulated entities exist. For instance, gravitational waves or black holes or strings. This is the stance of theoretical physics, or physics in general. You on the back, you have in the back of your mind, you've got all the accepted theories, and then a new theory comes up that postulates new things, and then you ask the question as a physicist, not as a philosopher, as a physicist, do these damn things exist or don't they? And that's been a discussion since Copernicus. Right? This has been a discussion in physics all the time since Copernicus. Something new is introduced, and then you ask the question, does that really exist, or is it purely a calculational device? And the question is, sometimes it's difficult to say. So I remember, as I said, I started with physics in '66. I heard a lecture by a guy from Hamburg, I don't remember his name, on quark physics at that time. In '67, winter term of '67, Heisenberg was there, sitting in the first row in the middle, and then this guy gave his talk. I didn't understand very much. I understood the word quarks came up again and again. And then Heisenberg stood up at the end of the lecture, and he said something I didn't understand for 5 minutes, but I still remember his last sentence when he said, and by the way, quarks don't exist. Right? Well, even Heisenberg may be wrong. So if you have a Nobel Prize, don't be sure that you'll be right afterwards all the time, although many Nobelists think that, but that's a different story. Okay, so this is the question in theoretical physics, and the question at that time was, can we believe in quarks, or is it a purely mental construction, a calculational device that may be useful, but to which nothing corresponds in reality? You've got this problem in physics again and again and again, with every time you introduce some sort of potential, a potential field, and that's a very nice device in physics. You never know, at least in the beginning, does that really exist, or is it simply a calculational device in order to treat the differential equations in a more elegant way? So this is the question that you pose in theoretical physics. Now here is the more radical stance 2, what I'd say. Believe in common sense things and ask whether physics is in general justified to postulate the existence of theoretical entities or theoretical structures for that matter. So on board in this talk is also structural realism, not only scientific realism, so-called scientific realism. Okay, this is the stance of the mainstream scientific and structural realism debate. So people assume that the entities are a common sense thing, they do exist, and then they ask, are we justified then to conclude from that and the physics to the existence either of entities, theoretical entities, or then those who deny that, they say, yes, but we can perhaps say that the structures are real, whatever they are. Okay, that's the second stance here, and there's an even more radical stance, because what you see here, you do not doubt the existence of common sense things. But I mean, in philosophy you can also doubt that and say, well, common sense things are a construction of whatever, transcendental ego, of our brain, or of society, or special communities, whatever it is, and then you can ask this question, and then you are even more radical, and you're not just accepting that for the sake of argument, but you say you question already common sense things, and of course theoretical entities, and this is the stance of a general realism debate. For instance, if you do it in a neo-Kantian perspective or in perspectival realism, you are putting your doubt also on the everyday objects that we in these other stances take for granted. So it's more radical, and it's just 3 different sorts of discussion or discourses that go on, and one should distinguish them. It seems to me extremely important to have such a distinction, because otherwise you cannot really understand many debates that go on in philosophy. Now here's the title question. Asking the title question, are there good arguments against scientific realism, implies going beyond stance 1, because that's not a question that is asked within physics. It's a question that's asked in philosophy, and this is a discourse different from stance 1 because of different presuppositions, right? So the philosophers or the physicists asking a particular question have different presuppositions than we have, be it physicists or philosophers asking this general question. And in the following I shall look at two arguments of strategies in defense of scientific and or structural realism, and these arguments are well known to you. It's the miracle argument and it's the new selective strategy. So this is the next step, and because that step is so difficult I have to have some order. All right. Now let's start with the miracle argument, and there are some defenders of the miracle argument in this audience, and whenever I give this sort of explanation of the miracle argument, I'm also a defender of the miracle argument. It's such an incredibly sweet and nice and especially true argument, so it appears. So what's the miracle argument? Science has been very successful again and again in producing novel predictions from theories which were not used in the construction of the respective theories, and these are the so-called use novel predictions. And the examples, I take two examples that are not so well known in philosophy of science, but which are just smashingly convincing arguments. It's the quantum theory, the covalent bond, Heitler in London from 1927. That paper was written in Zurich, by the way, and I teach in Zurich at the moment, but there's no connection to that. And that's the beginning of numerical quantum chemistry. So it's a whole branch, a whole science, and that was really, the covalent bond was really a breakthrough. Really, then finally, chemistry was shown to be, in a sense, one has to be careful, a part of physics. But there is no genuine chemical interaction that cannot be understood by the means of physics, namely the covalent bond, and that was a wonderful use novel prediction of quantum theory. And here's another one, and it's an accident that I mentioned it already, the gravitational waves and black holes. There are use novel predictions from general relativity from 1916. So when I started studying physics in 1966, 50 years later, I think it'll take 50 years until this damn stuff will be detected, and here we are. Okay. This was also a use novel prediction, but unfortunately I haven't written it down, so I can't really use it as evidence. Okay, so the miracle argument, is how can this sort of success be explained? I mean, this is really amazing. These use novel predictions of that size, right? You have to wait 100 years to get the real evidence. How can this sort of success be explained? Well, use novel predictions of theory can be explained on the basis of their approximate truth. There is, of course, of the theories. Why? In successful theory, the really existing objects of the world are at least approximately correctly represented. You've got referring theoretical terms, and the predicates by which you describe these entities are then approximately correct, and therefore use novel predictions about them are possible. If you hit at the right stuff, and then you say, okay, let's play around with the properties, and then you may come up with something new because you hit something real, and therefore you are able to make use novel predictions. However, from the perspective of anti-realism, such use novel predictions have no basis whatsoever, right? They would be sheer luck, or in other words, they would be an unexplainable miracle. And as science has emancipated itself from Christian religion, which did not happen in the 17th century because there it was full of theology. You cannot understand what a natural law is without theology in the 17th century, but we left that, and the physicists have forgotten that they're all theologians, but that's a different story. Now, here, I mean, it would be sheer luck, it would be a miracle, and and we don't believe in miracles anymore. There are no miracles. Anti-realism is not correct, but approximate scientific realism is. That's the miracle argument. And I want to test now, a sort of test, I mean, like the economist tests test economic assumptions by models, and they sometimes use toy models, and the question is then, I mean, how informative is the model? So I have a model situation here, and in this model situation we look what the miracle argument does here. And the model situation is this: imagine a situation in which there is a true function which we want to find out by measurement. So imagine it's a natural law, whatever it is, and we want to find out this, and the fact is, in this model situation the function is determined by 15 data points in 5 intervals, so then there is no leeway for the function, it's just fixated. So you may say it's a function with 15 free parameters, and then you have 15 data points, then you can determine the 15 parameters, and it happens to be in 5 intervals, but this is something we don't know, only God knows, right? So we're still in theology as physics has ever been. So this is God's view now. Here also God uses Cartesian coordinates. I happen to know that. You may not be aware of that, but I am. So here are the Cartesian coordinates, and that's the true function. And it happens the way that here are in 5 intervals are the data points, and they determine the true function, right? And this is God's view of the thing. He said, I made this natural law, and if the humans, the earthlings, can measure these 15 data points, they got the true function. So let's see what the earthlings are doing. Now imagine we earthlings have measured the first 6 data points because we want to determine the true function, right? We want to know what that function is. So we measure them, and of course on the basis of these data points there are many functions that fit not only the true function, right? You just have the data points and then you put a curve in it, so it's an exercise in curve fitting. So here we are, the 5 intervals, then here are these measured data points, and then we take curves and fit them into there. So this is one, this is another one. Of course we don't get the true function. I mean, that would be very, very strange, right? Because we got 6 data points only. So we get some sorts of points, and this is how it is. Okay, now imagine that we play around with that situation, and in the course of our curve fitting exercise, we come up with the following curve f star. So f star is a special function, therefore it's got a star. So here we are, and you know f star is even here now, and here we have the measured data points, right? And then we come up with that function. It's also a nice one, right? It's perfect, it's fitting these 6 data points, and here we are. And now we may say, why don't we make some novel predictions in the 3rd interval of data points on the basis of that function f star? Why don't we do that? Let's try it, okay? So here you go. So we do the following. Here we are, measured data points. Here's our curve. And now we go to the 3rd interval, which may be, for instance, 2 magnitudes more accuracy or whatever. The data, I don't say anything about the data. They may be just extremely more accurate, different part of the universe or whatever. So we make 3 measurements here, and these are the predicted data points. And look at that. They are just on this curve. They happen to be on this curve. Now, as it turns out, the predicted data points are empirically correct. That's wonderful. We made a successful use novel prediction with our function f star, right? This is a great success. And here are the over-optimistic realists, to which I do not belong, right? I'm not over-optimistic. The over-optimistic realists will go, f star is the true function. What a success! But we will say, let's be cautious and make another use novel prediction on the 4th interval of data points with that function f star. So we make a second just to test it. You know, you never know. You know, the universe is a very strange place. So we make a 4th round then of measurements. Here's our functions. We measured. There we get the function. Then this is predicted data points in the 1st round. And then, because we are very, very cautious, we make predicted data points in the 2nd round. You know, and we make use novel predictions. As it turns out, the predicted data points are again empirically correct. The second time we make an independent use novel prediction, we made a second useful novel prediction with our function, and now every realist, of course me included, will say f star is the true function. Everything else would be a miracle. How could you do that on the basis of 6 data points? We make twice successively use novel prediction. It would be a miracle if that wasn't the true function, of course. Unfortunately, we cannot measure the data points in the fifth interval so far, but perhaps in 100 years from now, 50 years from now, which are the relevant intervals in physics, as I explained to you. So we may measure data points in the fifth interval, but God, of course, has the full picture, you know, observing us and helping us, holding his hand above us, that nothing goes wrong, also not to the realists or to the anti-realists. And here again, the measured data points, this was our curve fitting, and then we had predicted data points, twice 3 data points and another predicted data point, and the unknown data points, well, they are there. Well, the true function is this one, right? So we had a function, we could twice predict, out of sheer luck of course, predict twice using over predictions, but unfortunately if we come to this interval we will see that it's not the true function, it's the wrong function. So what happened here? Well, unfortunately f star is badly different from the true function in spite of its twofold use over predictions, right? So we would accept, of course, the miracle argument, say, well, why? How can that happen? Well, in the model situation, we must be very lucky to hit upon a function that produces use over predictions in the third and fourth interval. That's quite clear, and I choose, of course, f star because I was so lucky to choose it. But you must be vastly more lucky to hit among these upon the true function, or only the approximately true functions, right? So you've got to be lucky to find one in the model situation that makes use over prediction, but you must be even more lucky, much more lucky, among those that do the prediction in the third and fourth interval than to hit upon the true functions. So in other words, there are in this model situation many more terribly false functions producing use novel predictions in the third and fourth interval, then there are approximately true functions with the same predictions, right? And this sheer amount, the larger set of these false functions is that if you hit at one that makes use novel predictions, it's much more likely that it's a false function, because the probability is much lower to get at the true function. It's many more things it has to fulfill. That holds for the model situation. I'm sure this is only a model situation, right? It's not reality. But has the model situation anything to do with real science? That's now the important question, because that then decides whether that is something which we should take seriously, or whether we say, well, this is a logician, a mathematician, you know, playing around, not understanding anything about science, and therefore coming up with these stupid examples. Okay, now compare use novel predictions in the third and fourth interval in the model situation with classical mechanics for 150 years between circa 1740. This is when Newton's theory was accepted, and the French astronomers and mathematicians began playing around with it and started calculating things, although the metaphysical grounding was very shaky, nobody understood it. And something like 1890 when the first doubts came up, so in an interval of 150 years, which was the era of classical physics, with extremely successful use novel predictions, applications in thermodynamics, acoustics, gravitational theory, prediction of new planets, and so on and so forth. So this is exactly the same situation, and therefore physicists at that time, following the no miracle argument, said most physicists thought that classical mechanics was the last word in physics. You all know this story about Planck, who was told in 1870 or so, don't study physics, physics is finished, you know, do something serious, and don't do physics, it's just not interesting. Until special relativity in 1905, general relativity in 1915, quantum mechanics 1925 entered the scene, corresponding to the fifth interval, because you could measure different things, right, which you didn't see before, but you extrapolated from what you could see, could measure, extrapolated to the fifth interval, and the fifth interval is a mess, right? We don't understand what's going on there. Okay, the intermediate result is this. And you see, I've write it as a conditional. In situations similar to the model situation, the miracle argument does certainly not work. It's certainly absolutely misleading. Does this answer the title question, are there good arguments against scientific realism? Of course not. That's not an answer I'm giving here. I'm just showing you this is interesting here. However, if people say this is the ultimate argument for scientific realism, and this argument may badly fail, then you think, that doesn't look too good. You know, it's not a smashing argument, but if the ultimate argument of those defending that, and then you can show that the ultimate argument, which should really make the case clear, if that collapses, well, then it doesn't look so good. It's not a watertight argument. I'm just saying, well, let's be a little careful. However, I mean, this is just one argument, and I mean, some people have called it the ultimate argument, but not all of them. More cautious people would never say this is the ultimate argument. This is just one argument. It's important, yes. But okay. So there may be other arguments for scientific realism besides the so-called ultimate one, and there may be other realisms supported by different arguments, and I want to now go to the now more fashionable and more up-to-date strategy of argument, namely the new the strategy which is called selective realism, and that covers a whole bunch of positions and a whole bunch of arguments. Now, selective realism, I give you a rough sketch of the strategy. I hope that I don't misrepresenting it. I'm trying to get all these arguments in their strongest form. I'm not trying to build up a straw man and then kill it. You can do that as a grad student, but not in my age. So the rough sketch of the strategy is this. Here's the presupposition that the realists share, and if you don't share it as a realist, you should, go somewhere. Namely that most, if not all, of our best theories are strictly speaking false. I mean, this is really what the scientists mostly believe. So you cannot interpret them realistically as a whole, right? As a whole, they are strictly speaking false. But, however, some of these theories are remarkably successful with use-novel predictions, right? This is a fact also. And then you say, come on, can we understand this remarkable success of these theories regarding, for instance, use-novel predictions, but you may also take other successes if you want. And the strategy is then select those parts of the theory responsible for the success, right? Identify what makes these theories successful, and then that's the further step. Then after you have identified these elements, then you say they are worthy of a realist commitment. Why? Because they are the cause or the reason why you could make these wonderful novel predictions and all the other successes. And then you say, well, that's a good candidate, for a realist commitment. And but you've got to be very careful how you pick out, how you select these things. And then you may run a final test on these commitments. Namely, you say the final test is then the survival of those parts through theory change. And that's the continuity argument. You say if these things really are responsible for the success of the theory, and the later theory, the successor theory, is also successful and even more successful, then it should be the case that that successful part of the earlier theory should be retained in the later theory, in whatever form, right? There are different possibilities, and that's the so-called continuity argument. And here are different versions of selective realism. So if you still stick to scientific realism, you must manage to keep the postulated theory entities stable through theory change. People deny that, and other people say, no, they are stable enough, and you must have a theory of reference, or whatever you do. If you manage to keep these things stable enough, then you are a selective realist in scientific realism, and you say, yeah, the entities themselves, they are stable, and I find them after the next theory change. I find again atoms and electrons and fields and whatnot. So if you manage to do that, then you can argue for scientific realism on this basis. Or you go to what is called explanationism, and you distinguish the idle parts versus the working posits of theory. So you dissect the theories and look what part is really responsible, and you don't say in advance a priori whether it's structures or you just leave that open and say, this is my strategy. I just identify the working posits, that parts of the theories that do the work of these use-novel predictions, and you identify them and then say, this is what I want to have. That's explanationism. And also structural realism is a different variant of selective realism. You just look at the relations, but you don't take just all and any relation, but those that are operative. Right? Operative meaning that it's really these parts of the relation that do the use-novel predictive work. You identify that. And then it's relations between entities, and there's of course a discussion whether the entities are needed for these relations or even without the entities, whatever, and that's, as far as I can see, the hottest candidate these days. That's mostly discussed in the literature. So what you see is that you have the success of theories in mind, especially the use novel predictions, and you say it's not the work of the theory as a whole, but it's the work of parts of that theory, and I want to identify those parts, and then I test whether these parts are good candidates for realism, that I say they should be conserved or preserved through theory change, and they should be visible again in the next generation of theories, and of course in the next generation of theories. That's the sketch of the argument, and that's of course very plausible. All right. Now I shall focus on what I call the final test, the continuity argument, namely the survival through theory change. That you have to have. I mean, if you identify and say, well, this is responsible for this wonderful predictive success, and then you look at the successor theory, and that element is not there, something completely different, right? That's also responsible for predictive success. Then you say, wow, well, I can't believe in that stuff because the newer theory is better. So I can't believe that this stuff is the one worthy of realist commitment. So you've got to look at this continuity, otherwise you don't believe in it. And this is an argument, this continuity argument is in implicit and explicit forms in all of these realisms that I looked at least. So if you have a somewhat more careful formulation, it's Johannes Fotz's from 2011. The continuity argument reads, he has a paper there on the continuity argument and refines it, and this is the final take at it. Preservation through theory change is a reliable guide to approximatory truth. So it's not a guarantee, but what he says, it's a reliable guide. This is where you have to put your bets. This is the best way how to put your bets as a realist of whatever kind. Now, I doubt that this is a reliable guide, and the argument I have here, I call the dead-end objection. It has had a different name, but you know, when people in arguments grow up, they change their name sometimes, they get married and things like that. So I used to call it the impasse objection, but this is the better term, it's the dead-end objection, right? Now, the dead-end objection, der Sackgasseneinwand. In German, it's almost nicer, right? Now, in order to articulate this dead-end objection, let a sequence of empirically progressive theories be given, empirically progressive new novel predictions, blah, 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 whatever you want, take whatever you want, be given with entity continuity or working posits continuity or structural continuity, whatever your favorite object for realist commitments is, and therefore I generalize immediately X continuity, right? You have something X, maybe properties, particles, whatever, entities, structures, working posits, whatnot. It's called X, and of course you have to have, this is the content of this final argument, you have to have this continuity through theory change. So you have X continuity. The X's that survive the theory change are thus the candidates for the realist commitment, and this is the argument by Fotzis. That's a reliable guide then to put your realist commitments on those X's. Now, for the sake of argument, and this is only for the sake of argument, let's make the temporary assumption that the given X continuity is due to the convergence of the sequence of theories to a certain limit theory. Some realists say that that's convergent realism, right? That there are many difficulties with that limit and how you see that and what it means and blah, blah, blah. But it's certainly not logically inconsistent to say that, and there I make the temporary assumption, and that helps you then to see what I'm after if you make this temporary assumption and later we kill it again. So the given X continuity is due to the convergence of the sequence of theories to a certain limit theory, and you see that already in the earlier members of that sequence. Now the realist must, and possibly happily will, those that do, the belief in convergent realism, must claim, and possibly happily will claim, that the limit theory is at least approximately true. Of course he can say that doesn't work, I don't believe in limit theory, but I'm saying, yeah, let's temporarily assume that just for the sake of argument, and some realists will be happy and say, oh Paul, you are so open-minded, you even accept the limit theory. That's right, yes, I love it. Okay, here it is. So, the limit theory. And the realists, of course, course, is then committed to say it must be approximately true. Otherwise, he wouldn't be justified to say that the continuity is the source of a realist commitment. So that what you see in the limit theory, of course, these x's, they must be approximately true. Now, the problem is this, and this is the dead-end objection. It should be excluded that the limit theory is a fundamentally false theory that is empirically very successful. And by empirically very successful, say all its empirical predictions with more than 10 to the minus 30 relative accuracy. So much more accurate than any of the theories we have. As I said, general relativity, we've got 10 to the minus 21, so I took 10 to the minus 30. In an earlier paper, I had 10 to the minus 100, but I thought I don't do that. That may shock you. I mean, such a tiny number, that won't go down well. Okay, so I stick to 10 to the minus 30. It's still 8 magnitudes better than general relativity. And by fundamentally false, I mean that some of the limit theory's x's are radically false. So not referring if it's entities, not existing working posits, not existing structures, such that these x's in the limit theory do not even approximately represent nature. Yeah? So you can see then from this sort of limit theory that explains why the members of that series of theories have this continuity of x, because already you see the property of the limit, you see them already in this series of finite theories, but unfortunately this limit theory is radically false in the intended ontological sense. Now, my problem is that I have with the realist that I don't know how you can exclude by any sort of argument the fundamental falsity of that limit theory. I'm not claiming it's clear that the limit theory is false. I'm just saying, yes, of course they could, the continuity of these x's could be a sign that the limit theory is a true, approximately true theory. That makes, I cannot exclude that, but I cannot exclude it that it's a radically false theory. I simply don't know. I don't have any information once I have a convergence of these theories what the properties of the limit theories. I just don't know. It's just an open question, and therefore the x continuity in a sequence of empirically progressive theories may be due, and this is now more generally, now I drop the assumption of the limit, but now you may find that sentence here plausible, that statement. It may be due to their common kinship with an empirically even more successful but still fundamentally false theory. That's the problem. So if you see some continuity, there may be underlying something which is even more successful, and there may be even conversions, and there may be no conversions, whatever. But that underlying empirically more successful stuff may still be fundamentally false. So the success doesn't point you to a realist commitment, but it just tells you, well, there must be an underlying theory somewhere that's even more successful. But that's all, and you don't know how successful it is, right? Especially you don't know whether it's the limit theory, and therefore this continuity of x through theory change, and even if you identify it as the source of the Hughes novel prediction and all that, it is not a sign of verisimilitude. It's just a sign there is something underneath, but you cannot say whether you are allowed to realistically interpret that or not. So here's my conclusion. I'm almost right in time. At the bottom level, both the continuity argument and the miracle argument share the same, and I dare say, fundamental weakness. And the fundamental weakness is this, that from even repeated Hughes novel predictions by our theory, that's the first part, or from continuity of x through even repeated theory change, no realist conclusions are drawn, can be drawn, because they can be due to something else, right? And you've got to be very lucky to have, of course, a false theory that makes true predictions, but you've got to be even more lucky to find a true theory that makes true predictions, right? This is the argument. The realist conclusions are over-hasty because the observed behavior could equally well be due to underlying fundamentally false theories, and that should be excluded, and I don't see any way how to be able to exclude that. In fact, my model suggests that there are many more false theories producing the observed effect than there are true theories. So you've got to be lucky anyway to find such a false theory, but you've got to be even much more lucky to find a true theory. And therefore don't believe in your luck. It would be a miracle if you find the true theory, right? It would be an absolute miracle. I don't believe in miracles, okay? So second, my title question was, coming to the conclusion, are there good arguments against scientific realism? The answer is, perhaps. At least some arguments for scientific or structural X-realism are not very convincing, but that's of course no answer to the title question. Thank you very much.